In this video, we are going to discuss projectile motion. And projectile motion is very similar to free fall, only now we're adding in X motion into addition to the Y motion. So the Y motion is going to be exactly the same. You're going to see the velocity decrease as you go up, be 0 at max height, and then come back down with increasing magnitude of velocity, but now in the negative direction. But now instead of going straight up and coming back down, you're going to move forward at the same time. And so the motion is going to end up looking parabolic. Now, once again, the only force acting on the object is going to be the force due to gravity, which is going to cause that decrease in velocity on the way up and increase in the negative direction on the way back down. This means that once again we are going to neglect air resistance. So once again, these problems cannot involve rocket engines being attached to the object that is in motion. And this is going to be flight through the air. But once again, we're ignoring the fact that the air is actually there. And as I said before, the motion of the object will be parabolic in shape, so not a straight line. It will be arced. Alright, so in this portion of the video, we are going to look at a simulation of some projectile motion. So the first thing I want to do is show you the difference between having air resistance and not having air resistance. So right now we have air resistance turned off. And I'm going to fire. We're launching a pumpkin. So the pumpkin's going to fire. Now I'm going to turn on air resistance. And I am going to launch again. And you can see when we have that additional force included, which is very difficult to actually calculate, you do not go quite as high or quite as far. Alright, so let's turn air resistance back off, because in this course we're going to ignore air resistance. And let's erase our paths. Alright, so right now we're going to focus in on acceleration. So we're going to show the components of the acceleration. Alright, so we're going to fire. And notice that the acceleration is pointing in the negative y direction still. And the reason for this is, remember, the only force acting on the object is the acceleration, is the force due to gravity, which remember acts towards the center of the earth. There is no acceleration in the x direction. There's nothing pulling the object sideways. Now let's look at the velocity. So let's focus on the y direction first, because that's the one we're most familiar with. So in the y direction, you see it's shrinking, go to 0, and then negative and increase. So let's do that again. So notice it's decreasing, pointing in the positive y direction, goes to 0 at max height, and then comes down in the negative y direction. Now let's focus in on the x direction. Notice the arrow is not changing the whole way through the motion. So it has the same initial velocity in the x direction the whole way through the motion. Same initial velocity at the beginning, at max height, and at the end. The velocity in the x direction does not change because the acceleration in the x direction is 0. That's why it can move forward, because it just has that forward velocity. So we can see the connection here between acceleration and velocity. When the acceleration is 0, we have a constant velocity. When there is an acceleration, the velocity is going to change. And in this case, because the y is the one with the acceleration, and it's the acceleration due to gravity again, you are going to see the same thing that you saw with free fall. Now, another thing I want to point out that I pointed out on the prior slide, and that's the idea that this is a parabolic path. And there's often a habit, because you'll be given the delta x, so the range, and the delta y, or whatever the height is at the particular position you're interested in, and you want to use Pythagorean's theorem, connecting from here to here, making it a right triangle. But notice that it's not a straight line. It's not a straight line. It's not a hypotenuse. It's curved. And so sometimes you might get an answer that's close, but it's not the correct answer because the path is not a straight line. It's not the hypotenuse of a triangle, it's a curved path like a parabola. So please do not try to use right triangle trig to solve projectile motion problems. At least not with the delta x and delta y. We're going to use some of that with the velocity later on. The other thing I want to point out is, it's nice with this one I have set up here, there's a certain amount of symmetry. Where you start here at some y above the surface, it happens to be 0. You go up and max height is exactly at the center. So if we take a timer, let me get out the timer. And I can put the timer at different positions. To get to max height takes 1 second in this case. And then to get back down here, we're at almost 2 seconds. So the first half of the journey and the second half of the journey, so to get from the ground up to max height is 1 second, and to get from max height back down to the ground is an additional 1 second. So we have symmetry to the motion, where here you would have some positive initial velocity. Here you would have 0 in the y, but there would still be an x velocity, but you would come back down to the same velocity, only now in the negative direction. There's symmetry to this motion. And because you're going from the ground back to the ground, the delta y for the whole motion is actually 0. And half of the delta x for the whole motion will get you the delta x of max height. So it's really nice when you have symmetry, so you can use those, draw yourself a picture, and understand those relationships where half of the motion is up to max height and the other half of the motion is from max height down to the ground. However, if you're not in a case where you're going from the ground back to the ground, that symmetry does not exist. So let me erase this, and we're going to launch again. So let's see, that's the measuring tape. I don't want the measuring tape. I want my timer here. There's a little green dot you might not be able to see that tells me max height. And once again, it's a little under 1 second. And then I can come back down here, and it's 2.5 seconds. So it takes longer to get from max height to the ground than it did to get from the initial position up to max height. So this symmetry no longer exists, so you have to be careful of that. And I also want to point out that the final velocity is not 0. For one, you have constant velocity in the x direction, and remember the velocity in the y is increasing in the negative direction on the way down. And we exit the problem just before it hits the ground. We're not yet equipped to deal with the force of the ground hitting the object, or the object hitting the ground and experiencing a force due to that collision. We're not equipped to deal with that yet. So we're always going to exit the problem. So anytime you're asked about a projectile motion problem, do not assume that the final velocity is going to be 0. The only time it's going to be 0 is the y component at max height. Alright, so let's summarize what we just learned in the prior video. The acceleration in the x direction is 0 meters per second squared. That means that the velocity in the x direction is constant. So v initial in the x is going to equal v final in the x. The acceleration in the y is equal to a negative 9.8 meters per second squared, which is the same thing as g. So sometimes in equations you'll see it written as g, sometimes you'll see it written as a of y. They mean the same thing in this case. So this means that the velocity decreases, but is positive on the way up, and the velocity increases but is negative on the way down. and the velocity in the y direction is 0 at max delta y. Not that delta y is 0, but the velocity when delta y is at its maximum value is 0. So let's see what this does to our kinematic equations that we learned in topic 2. Let's start by working in the x direction. Our first equation would be velocity final in the x equals velocity initial in the x plus acceleration in the x times time. Now, you'll be given an initial velocity, or you may be asked to solve for it, but anyway, there's an initial velocity involved. And you're going to be given a theta. And this theta is always relative to the positive x-axis. So it's how many degrees the object is moving initially above the positive x-axis. So if you're moving along the positive x-axis, that angle will be 0. This means that if we draw a coordinate system here, we're going to have some velocity initial here, and this is going to be theta. So this would be velocity initial in the x, velocity initial in the y. So using trig functions, I can say that velocity initial in the x is equal to velocity initial times the cosine of theta, and velocity initial in the y is equal to velocity initial times the sine of theta. So I'm going to make that substitution in there for you. That way you don't always have to separately break the initial velocity down into components. So velocity final in the x is going to equal velocity initial times the cosine of theta, and we just said that the acceleration in the x was 0. This means that anything times 0 is 0, so velocity final in the x is going to equal velocity initial times the cosine of theta. And we already knew this, and I wrote this down on the previous slide, the idea that the initial and the final velocity in the x direction are exactly the same because the acceleration is 0. The next equation we want to look at is that the delta x is equal to velocity initial in the x times time plus 1/2 times acceleration in the x times time squared. And all I'm doing is I'm writing the kinematic equations, and anything that's a vector quantity, I'm just writing down the x component. So I'm just putting a lot of x subscripts. So remember, delta x is the horizontal distance. And I'm going to sub in vi cosine of theta for the velocity initial in the x direction times time, plus 1/2 times 0 times time squared. Anything times 0 is 0, so that equation reduces down to velocity initial times the cosine of theta times time. And it turns out there's only 2 relationships for the x direction. The other kinematic equations will result in the equations we already have written here. Because there's no acceleration in the x direction essentially you just move forward. Velocity is constant and you move forward. The y direction is going to turn out to be slightly more interesting. Alright, so now let's talk about the y direction. Start with our first kinematic equation. Velocity final in the y equals velocity initial in the y plus acceleration in the y times time. And all I can do here is sub in for the initial velocity in the y that we saw on the earlier in the video, that is velocity initial times the sine of theta, plus we can say a of y or g. So this tells us that as time progresses, our velocity is going to increase, or decrease I should say, until 0, and then come back down increasing, but in the negative direction. So this is the equation that gives us that behavior with the velocity. Alright, so let's look at our next one. Delta y is going to equal velocity initial in the y direction times time plus 1/2 times a y t squared. So all I can do here is sub in the vi sine of theta times t and write down g for a of y. And this is what gives us our parabolic path. The idea that the delta y changes as t squared. Alright, so let's look at our other kinematic equations. So once again, all I can do is sub in VI sine of theta and G for the acceleration. Let's see, there should be one more. Delta y equals 1/2 times the quantity v initial in the y plus v final in the y times time. And I can sub in the initial sine of theta plus vy times t. And all you're using when you're doing problems with projectile motions is the equations that I have squared. I'm not going to ask you to later derive where those equations came from. Your job is to learn how to apply them. Keep in mind, time is not a vector. So if you have an object that is flying through the air, and say I ask you about something that happens right here, you'll have some delta x and some delta y. However, the object actually goes like this. It isn't like there's a separate time for x and a separate time for y. The object goes like this, and it does the motion all at once. So there's a single time. So the time in the x direction equation to get to here is the same as the time as the y direction equation to get to here. There isn't a separate tx and a separate ty. So keep that in mind, that links between your x and your y equations, because time is not a vector. The other thing I want to point out is that we have v final in the x and we have v final in the y. Those are components of the final velocity. They're not individually the final velocity, which means that once you have v final in the y and v final in the x, you would have to do essentially the end of the component method, where you would add r of x and r of y. Well, let's say it's an object falling downward. So we would have a positive v of x final, and we would have a negative v final in the y. And so you would have to use Pythagorean's theorem in order to find the final velocity. And you would have to use inverse tangent to find the direction of that final velocity. So keep in mind, the components are not the actual final velocity. You need the magnitude and direction using that tail end of the component method, or the analytical method, where you're using Pythagorean's theorem and inverse tangent to find magnitude and direction.